Hi there, I want to give the honors classes some extra details about the bond angles in molecules. So we do have these three parent geometries, linear, trigonal, planar, and tetrahedral. And if those are the actual shapes, those would be the true bond angles. Okay, so in your linear molecule, that would be 180 degrees in the bond angle. So these two white atoms would be separated by each other by 180 degrees. In a trigonal planar molecule, all of the angles going around here would also be 120 degrees. Okay, so all of those, 120. Okay, and in the tetrahedral molecule, it's a little bit harder to draw arrows in all directions here because I'd have to draw, goodness, how many arrows would I have to draw? 1, 2, 3, 4, 5, a lot anyways. 1, 2, 3, 4, 5, 6, I think. They would all be that irrational number, which is really close to 109.5 degrees, okay? But the effect of lone pairs is going to alter these bond angles a little bit. And so something you need to know about lone pairs is apparently they take up a little bit more space. They're a little bit more repulsive. They occupy a bit more volume than bonding pairs. Okay? And that sort of makes sense if you think about it, because when you have a chemical bond, you're really limiting where those electrons are going to go. They tend to hang out in the middle of the two atoms. These two electrons drawn here would be attracted simultaneously to the blue atom and to the white atom. And so they tend to hang out here in the middle, although there is a little bit of a probability that they could move around outside. They mostly hang out in here. Whereas with a lone pair, the lone pair is only attracted to that blue atom. That's the atom that it belongs to. And so they kind of swarm around way out here like this. Okay, so they really do take up quite a bit more volume than these bonding pairs do. Okay, so lone pairs occupy a bit more volume. And as a result, when you have molecules with lone pairs, the effect on the bond angles is going to be important to consider. Okay, so they tend to compress bond angles down. Okay, so the bond angles that are present in the molecule get compressed together. So what we have to do is consider the parent geometry and then think about what the effect of a lone pair would be. So, in a molecule with this particular bent configuration, okay, so here, let me just erase the whole thing and redraw it. An example of this that we saw this week is sulfur dioxide. Sulfur dioxide has this bent configuration. And so scientists have studied this substance, sulfur dioxide. And here's one of the resonance structures for sulfur dioxide. And we would predict it to be bent with a trigonal planar parent geometry. So VSEPR, we would kind of recognize we have 3 effective pairs of electrons around the sulfur atom, and we might expect this bond angle right here to be 120 degrees. Now scientists, they've actually gone and studied this substance, and so let's look it up on Wikipedia. Sulfur dioxide. And here's the Wikipedia entry for sulfur dioxide. And the bond angle, you can see, is really, really close to 120. It's 119. Okay? And so that's empirical. That's what it's actually been measured to be. Okay? And so notice it's been compressed down a little bit, from that theoretical 120. Now it's about 119. Now there are other molecules that have this shape. In general, we say having one lone pair is not going to affect the bond angle too much. Okay, so in this particular bent configuration, this bond angle is still really, really close to 120 degrees. And we know that empirically from experiment. And so we're still going to say it's basically 120. Sulfur dioxide's 119, but there's other molecules that are still really close to 120. So we're going to say one lone pair doesn't really affect the bond angles. But down here in tetrahedral parent geometry, there is going to be a particularly large effect. Okay, so in the tetrahedral molecule, for instance, methane, in the methane molecule, we actually know that these bond angles are 109.5, that irrational number, so really close to 109.5. In a trigonal pyramidal molecule, it's got a lone pair. And so lone pairs tend to take up a bit more volume. And so what would you predict is going to happen to these angles between the hydrogen atoms down here, like this angle down in here? This lone pair is going to compress those bond angles together. So let's look up the ammonia molecule and see what we know by experiment. I think the bond angle in the ammonia is about 107 degrees. I'll have to look that up. I think it's about 107 degrees. So it's been compressed down a little bit. And also, we'll talk about water as well. Water is a bent molecule with tetrahedral parent geometry. And, so you could draw its Lewis structure, or at least its shape, kind of like that. But it's a little bit easier to see the bond angle when we put it on its side like this. Via CPR, we would expect that bond angle to be about 109.5, and I believe it's closer to 105 degrees. Okay, so the parent geometry, 109.5, with one lone pair it gets compressed down to 107 degrees, and with two lone pairs it gets compressed down to 105 degrees. Okay, so with an extra lone pair, we get a bit more compression on that bond angle. And that makes sense, because if this lone pair is taking up a bunch of space in its electron cloud, and so is that one, it's going to compress things together even more. So let's confirm this, pulling up the Wikipedia entries for these things. We got ammonia and water. The ammonia molecule. Let's see. And the bond angle, they don't have it here up top. They've got to have a Lewis structure somewhere that's showing the bond angle. There's all sorts of other things they're saying about ammonia, but bond angle. Okay, so here in the structure, experimentally determined to be about 106.7 degrees, so close to 107 degrees. And in the water molecule, let's look that up. It's going to be, I think it's 104.5 or something close to properties of water. Let's do water molecule bond angle. They're predicting 109.5 from via CPR, but that's false. Molecular geometry, here we go. And they mentioned water. Water is actually their example here, 104.45 degrees. Bond angle. Let's see. With water. Here, For example, water has an angle of about 105. Okay, and that's a result of the two lone pairs. Okay, so that's important to know. So you have these theoretical molecules which result from pure geometry, and you tend to get those molecules when those angles when you have atoms bonded in that orientation. But if you have lone pairs, it's important to recognize that lone pairs occupy a bit more volume and they tend to compress those bond angles down. Okay, so uh, that's all.